Hello everybody, this is Cameron Snow with Danomics.com and we are bringing you another educational video today. And in this video we're going to be talking about total organic carbon, or TOC as it's often referred to. So first of all, why do we care about TOC? Well, the primary reason is that zones with elevated TOC are our source rocks that generate oil and gas. So the organic material undergoes thermogenesis. So, we heat it up. It then undergoes this process where it begins to expel oil and gas. That oil and gas then migrates into our target reservoir, which is what we drill and produce. Organic shells also are important reservoirs these days. So if you think about things like the Woodford or the Eagleford or the Vaca Muerta down in Argentina, those are all organic shells that are now, prolific producers thanks to fracking technology. And so that's why we care about TOC. So as I mentioned in the video on what petrophysicists do, petrophysicists make quantitative interpretations, but they also make qualitative interpretations. And so we're going to start off, we're going to make a qualitative assessment, and then we are going to migrate into making a more quantitative assessment here. So to do this, what we need to do is we're going to start off looking at our logs here and just reviewing a bit of what we see. So I'm looking at the same log as in the clay volume video. It's from the Powder River Basin, and we're going to be looking at the gamma ray to get started. And so when we look at the gamma ray, we see, modestly high gamma ray values in these shells as we come down. Then we see some significantly higher gamma ray values in a few of the intervals. And so, we could say, all right, well, these modestly high values are shells and these very high values are organic shells. And the reason one would make that interpretation is we know that shells, do have slightly higher gamma ray values than, things like clean sands or limestones. And the reason why is they often have elements like potassium in their mineral structure. And we can substitute in other large ions like thorium into the clay mineral structures. And that's what gives us these high resistivity values, the high gamma ray values that we see. High gamma ray values, because thorium is naturally, has radioactive isotopes, and those isotopes are what the gamma ray tool is reading. It's reading the radioactivity of the formation. Okay, so that explains why shells have higher gamma ray values. But what about organic shells? What specifically gives them significantly higher gamma ray readings? Well, the answer is in the fact that uranium likes to attach itself to organic particulate matter. And so, as you know, the uranium isotopes are radioactive. And so, we have uranium-235 and 238 on there, which as they decay, are creating this radioactivity. And that is why our organic shells have often significantly higher gamma ray values. And so when we take that and we apply that knowledge to our log, not organic, not organic, not organic, not organic, ooh, potentially organic, not organic, oh, maybe a few streaks here that are organic, and then once again another organic interval. So that is how we identify target intervals for deeper analysis. Then once we do that, there are a number of methods that we can use that are visual methods, like the Passey overlay methods. Those are methods that were originally published by Passey in 1990 in AAPG. It includes things like the Passey sonic method, which is probably the most referenced method, but it also includes things like the neutron and density methods. And the idea here is that inorganic shells typically have low resistivity readings, and the porosity readings are generally unaffected, by organic matter. But when you move into an organic shell, the porosity is affected by the organic matter, and you get often higher resistivity readings due to the fact that the organic material is being cracked into hydrocarbons and therefore is increasing the resistivity in the formation. And so it's looking at a combination of that excess resistivity and the effect on the porosity logs and using that to provide both a visual assessment of the presence of organic matter as well as a quantitative assessment. So with that said, how do we apply the PASI methods? What we do in practice is we come up here to one of these organic intervals, we look at the resistivity curve, and we set a baseline value in that curve. So in this interval, I've set it around 3.5 ohms, and we can see that in most of these shells, that is a pretty good value. And then we go through and we do the same thing where we find an inorganic shell, we drop our parameter in kind of the middle of that distribution for all of our curves here, and then we come down to our organic interval. Let's zoom in here. So in this case, the Niobrara formation, and we we look and we say, okay, elevated gamma ray, excess resistivity relative to the shells above it and below it, and then when we look at the actual porosity log measurements of the sonic, the density of the neutron, relative to what's called the delta log R overlay, or the log R overlay, we can see that we get visual cues for each of the PASI overlay methods, as well as the modified PASI method. So that is how we go about doing that interpretation. And this, once again, it's just giving us a visual cue, and then we'll go over how we convert that into an actual interpretation that's quantitative next. So I'm just going to pull up some of these slides here, and I'm going to start off with the PASI methods here. So okay, let's pull up the formula for PASI. So essentially, it takes the form of the ratio of the resistivity in our log to the resistivity of our baseline, and then plus the difference in our porosity curve baseline and what's actually observed. And so once we have that, that creates that delta log R parameter. We feed delta log R into our TOC equation. We combine that with a level of maturity, and that is how we calculate our TOC. So I know these formulas look rather complicated, especially this level of maturity one, but this level of maturity one is essentially just a curve fit from the literature. And you can go find the equations for all three of the PASI methods in his 1990 AAPG publication. And you'll notice out here we have, two parameters out here, our SF and our SO, which are a scaling factor and a shifting factor. And that's just because sometimes you're not able to get a good fit by adjusting your baseline parameters, and so people will go in and they'll apply essentially a fudge factor to get a match to their core data. Okay, so that is the, those are the PASI overlay methods. We also have the modified PASI method, which is, looking at the difference between our log resistivity and our bound water resistivity, essentially, so that RWNO, and then we're looking at that relative to our total porosity calculation, and then once again it takes into account this level of maturity parameter, which is the thermal maturity of the rock. Okay, and so that's the modified PASI parameter. We have Schmoker's method. Schmoker was originally performed on some of the Devonian shells in the Appalachian. It was updated from a study of some Bakken shells, and it takes this general form where you have two constants, A and B, and then these constants, they can be calibrated based on lab data for your specific formation, and there have been a number of studies that have taken this form of the Schmoker equation where they have localized parameters. So if you're going to apply Schmoker, you need to localize your parameters in this area. And then in terms of sonic methods, one that I like is called the Faust method. It's looking at the difference between um, the actual sonic porosity and a sonic porosity, yeah, a synthetic sonic porosity essentially. It's based on the resistivity, and this really highlights organic shells quite well. Okay, so if we jump back to the platform here and we look at this, so with the PASI methods, it's very easy to set these parameters. You find a your inorganic shell, you set these. With Faust, there's no real parameters to set. There is a fudge factor that can be used. But the real trick here is that you need to know your thermal maturity. That is the most important parameter. And so, without thermal maturity data, if you don't know if this rock is a 0.7 vitrinite reflectance, so here we're seeing, over 2% TOC versus a 0.5, where we're seeing, nearly 5 or 6% TOC versus something that's quite mature. So let's say something that's gas mature, so like a 1.2 VRE, where we have less than 1%. So, you have to have core calibration, or you have to have a very good regional context, because otherwise you're going to get an answer that is quantified, but it's going to be an answer that is uncalibrated and will start to really deviate away from the actual answer, as you move away from your control points. So that is TOC in a nutshell. Once you have TOC, so one important thing to remember about TOC is when we measure it in the lab, we measure TOC in terms of weight percent. But when we talk about kerogen, we talk about kerogen in terms of volume percent. So we need to do a conversion from weight percent to volume percent to get from TOC to kerogen. And that's a very straightforward correlation. You can find that in a number of websites here, but here I'm just going to show you like the general form that equation takes. You can set some baseline values for this, and then you can do that conversion. And then you'll have it in volume percent, which is then what we'll use when we're doing things like porosity corrections, or if we put it into a mineral inversion model. So I just wanted you to have that in mind as a reference there. And so, just a few helpful tips just to help you out with your interpretation. There's a few things that I always like to do. I like to go through and, I'm never sure which method is necessarily going to work best for basin, or for a particular interval or play. So what I like to do is I like to go through and do my visual assessment, identify visually where I think my organic shells are. I like to go through and I set my PASI overlay methods. I go through and I set my modified PASI method. And then I will start to do a couple of cross plots. So here I've got a cross plot of modified PASI versus the PASI sonic method. And we can see I get a pretty good correlation there. I also like to use the TOC Faust if I have a sonic log. And once again, what we can see is a reasonable correlation. And let me change my VRE here back to what I think the value actually is. We see a pretty good correlation between our sonic based method and our modified PASI based method. And so I like to go through and do a number of these cross plots to see that I'm getting a good agreement between all these different methods. And I also like to come in and inspect them in the log track and say, okay, are we getting similar patterns between these? And if not, what's driving that? And we can see that here in general we have pretty good agreement between all of our PASI methods and our Faust methods, so our sonic-based methods. And so that is essentially how we go about doing the TOC assessment in a rock. So the first step is identify areas of interest, try to sample those to get concrete rock data or get solid geological context so we know what the maturity is. Then go through and do your the overlay methods, so the passing methods, then your modified passing methods, your Faust methods. Try to get a good agreement between those and your lab data, and then extrapolate that outside of areas of your better control. So that's how you do a TOC analysis. I hope this video was useful. So thank you and goodbye.